Chapter 2, Basic Instruments and Measurements. Keywords and terms. The following words and terms will become important pieces in your electricity and electronics vocabulary. Look for them as you read this chapter. Ammeter, analog meter, common, Darsoval movement, digital multimeter or DMM, field effect transistor, volt-ohm-meter, VOM or FETVOMS, linear meter scale, multiply resistor, and the National Electric Code. Other words include nonlinear scale, ohm meter, ohms per volt, resolution, root mean square, RMS value, schematic, shunt, volt-ohm-meter or VOM. Electricity and electronics technicians rely on instruments to judge the actions and traits of a circuit precisely. The skillful use of instruments is the mark of a good technician and will enable you to quickly and efficiently troubleshoot a circuit. The student of electricity and electronics must know what he or she is trying to measure and how to measure it. In this chapter, we will discuss the three most common types of meters used today. These meters are the ohm meter, the ammeter, and the voltmeter. Each of these meters will be covered thoroughly to give you the basic skills necessary to continue your studies. Think of an electrical meter as an electronic ruler that is used to measure electrical quantities such as voltage, current, and resistance. The meters you will be using come in two formats. There are analog meters and digital meters. Analog meters, discussed first in this chapter, use a scale with continuous variable values. Digital meters give values in discrete amounts using the units 0 through 9. Digital meters are discussed later in the chapter. 2.1. Basic analog meter movement. A common type of meter movement measures current and voltage. It is the Darsoval movement or stationary magnet moving coil galvanometer, figure 2-1. The movement consists of a permanent type magnet and a rotating coil in the magnetic field. An indicating needle is attached to the rotating coil. See figure 2-2. When a current passes through the moving coil, a magnetic field is produced. This field reacts with the stationary field and causes rotation or deflection in the needle, which is attached again to the moving coil. This deflection force is proportional to the strength of the current flowing through the moving coil. When the current ceases to flow, the moving coil is returned to its at-rest position by hair springs. These springs are also connected to the meter coil. The deflecting force rotates the coil against the restraining force of these springs. Again, see figure 2-3. Caution: the coil that rotates in the magnetic field is mounted on precision-type jewel bearings, much like a fine watch. The jewel-type bearings and mount, known as a Darsoval movement, make the instrument very easy to damage if dropped or jarred. Extreme caution should be used when transporting or moving a meter with a Darsoval type movement. Figure 2-1 will show you a phantom view of the Darsoval meter movement. When connecting the meter to an electrical circuit, proper polarity must be maintained. The meter is equipped with polarity markings, usually the red plus sign and a black negative sign. Some meters use the abbreviation COM, C-O-M, which stands for common for the negative polarity marking. The meter rotates inside the permanent magnet field. If proper polarity is not used, the coil will deflect in the direction opposite to that which it was designed. At the very least, the needle will not deflect, and there will appear to be no reading. At worst, this situation could possibly damage the meter. So some meters have circuit protection built into them. This protects the meter movement from damage that can be caused by improper connections. Figure 2-3, you can see a current flowing through the ammeter must be limited by a resistance in the circuit being tested. The iron vein meter movement. The operation of the iron vein meter movement is shown in figure 2-4. Two pieces of iron are placed in the hollow core of a solenoid or a coil of wire. When the current passes through the solenoid, both pieces of metal become magnetized with the same polarity. Because like poles repel each other, the two pieces of iron are repelled from each other. One piece of metal is fixed in its position, the other piece of metal pivots. The pivoting piece can turn away from the fixed metal. An indicating needle is attached to the moving vein. The needle is equipped with hair springs so that the vein must move against the spring tension for accurate readings. An applied voltage causes the current flow in the solenoid and creates the magnetic field. The moving vein is repelled against the spring according to the strength of the magnetic field. The needle may indicate either voltage or current. It is calibrated for the magnitude or average size of the applied voltage or current. When the iron vane movement is used for a voltmeter, a solenoid is commonly wound with many turns of fine wire. The proper multiplier resistance may be used to increase the range of the meter. Multiplier resistance will be talked about shortly. A selector switch is used to select proper ranges. When used as an ammeter for current, the solenoid has a few turns of heavy wire. This is because the coil must be connected in series with the circuit and carry the circuit current. Regardless of the polarity of the applied voltage or current, the iron vane meter movement always deflects in the same direction. Either AC or DC may be measured with this instrument. Generally, this type of meter is best suited for high power measurements. Meter scales. The meter scale is used to interpret ampere and voltage values in the linear type. A linear meter scale has evenly spaced marks used to indicate the amount of current flowing or voltage present. In the meter movement, figure 2-5 shows a typical linear scale for an ammeter. The scale illustrated in figure 2-5 is marked from 0 to 5, with 10 smaller marks between each major numbered marks. To determine the value of each mark between the major divisions, the scale factor, divide the value of the first major division by the number of spaces in that division. The dial of the right of each scale, figure 2-5, is the range selector. The range selector must be correlated to that scale to determine full scale deflection. The formula for scale factor is as follows. Scale factor equals the value of major division divided by the number of spaces. Study figure 2-5. Note that the value of each division changes as the range selector changes. On the scale, the first major division is marked with a 1. In the top example, the range selector is set to 5 amps. This means that the full scale deflection is 5 amps. On this scale, the 1 represents 1 amp. There are 10 spaces between the 1 and the 0. By dividing 1 by 10, we can conclude that each space is equal to 1/10 or 0.1 of the first major mark, or 0.1 amp. The second example has a full scale deflection equal to 0.5 or 0.5 amperes. Therefore, the major scale markings are equal to 0.1 ampere each. Since there are 10 spaces between each major division, each small mark is equal to 0.01 amperes each, or 10 milliamps. In the third example, the range selector switch is set to 0.05 amps. This makes the full scale deflection equal to 0.05 amperes. Each major number division is equal to 0.01 ampere. Since there are 10 equal spaces between each major division in the scale, each small mark is equal to 0.001 amperes or 1 milliamp. Review questions for section 2.1. Another name for the stationary magnet moving coil meter is the Darson ball movement. Explain how a moving coil operates. Again, a moving coil of thin wire which has the needle attached to it. The pointing needle is fixed with a hair spring or hair coil of spring wire or material, and the voltage or current is channeled or directed through this thin wire, of course using a multiplier resistor to limit the amount of current or voltage through this thin wire, not to damage it. And once this voltage or current goes through this thin wire, thus through the coil, it is magnetized and it creates a reaction with the permanent magnet that's affixed to the outside of this rotating coil. And depending on the amount of voltage or current going through it, that's how much it will reflect. Again, limited by the coil of hairspring. So the amount of deflection depends on the amount of current or voltage going through this coil of wire, also called a moving coil or Darson ball movement. A linear meter scale has evenly spaced marks used to indicate circuit values. 2.2. Ammeter. An ammeter measures electrical current in a circuit. The ammeter will usually measure in amperes, milliamperes, or microamperes, depending on the scale design of the instrument. The coil in the meter movement of an ammeter is wound with many turns of fine wire. If a large current is allowed to flow through this coil, the ammeter will quickly burn out. In order to measure larger currents, a shunt or alternate path is provided for most of the current. Most of the current flows through the shunt, leaving only enough current to safely work the meter movement coil. The shunt is a precision resistor connected in parallel with the meter coil. The use of shunts is illustrated in figure 2-6. In figure 2-7, you will see the proper way to connect an ammeter to an electrical circuit. The ammeter is connected to the circuit. It becomes part of the circuit in order to allow the current to flow through the meter coil. To connect an ammeter to a circuit, one usually has to make an open or disconnect some device in the circuit. This allows you to insert the meter into the circuit. You're connecting the meter in series with the circuit or device you're trying to measure. Example, the specification of a certain meter movement requires 0.001 ampere or 1 milliampere of current for full-scale deflection to the needle. The ohmic resistance of the meter movement coil is 100 ohms. Compute the shunt resistor values for a meter that will measure for different ampere ranges. The ranges are as follows: 0 to 1 milliamp, 0 to 10 milliamp, 0 to 50 milliamp, and 0 to 100 milliamp. First, calculate the voltage required for full-scale deflection on the lowest setting, which is 0 to 1 milliamp. Using Ohm's law, voltage, or E, equals I, or full-scale current, times R, or resistance of the coil. So we have the current, which is 0.001 amp, or 1 milliamp, times resistance, which is 100 ohms. Using Ohm's law, voltage equals 0.1 volts. The meter will read from 0 to 1 milliamp without a shunt for full-scale deflection of 0.1 volts. So 0.1 volt is required for full-scale deflection again. To convert this same meter to read from 0 to 10 milliamps, a shunt must be connected that will carry 9/10 of the current. Thus, 9 milliamps of current will travel through the shunt, leaving 1 milliampere to operate the meter. The first step in the calculation is to determine that 0.1 volts is required for full-scale deflection. The shunt is connected in parallel with the coil, so it will have 0.1 volts applied to it. Since 0.1 volts must be applied across the shunt, and the shunt must also account for 9/10 of the current, you can apply Ohm's law to calculate the shunt resistance. Again, since 0.1 volts must be applied across the shunt, and the shunt must also account for 9/10 of the current, you can apply Ohm's law to calculate the shunt's resistance. So using Ohm's law, the shunt resistance equals voltage divided current. We know the voltage is 0.1 volt. The current is 0.009 amps or 9 milliamps. So the resistance is 0.1 volts divided 0.009 amps, which is 11.1 ohms. Again, where did the 0.009 amps come from? That is 9/10 of 10 milliamps, which is 0.01 amps. 9/10 of that is 0.009 amps. Where did the 0.1 volts come from? It is established that 0.1 volts must go through the shunt for full deflection. That's what we have as the voltage. The meter will require a shunt with a resistance value of 11.1 ohms for that example for the 0 to 10 milliamp scale. Figure 2-6 shows steps for the voltage for full-scale deflection of the ammeter. Step 1, the voltage that causes the full-scale deflection current is computed. Step 2, the shunt carries 9/10 of the current. Step 3, the shunt carries 49/50 of the current. And the step 4 carries 99/100 of the current. Bottom, basic setup of an ammeter with 3 shunt resistors. A switch selects the range. Figure 2-7, an ammeter is always connected in series with the circuit device being measured. The meter must be connected to proper polarity. To convert this meter for the 0 to 50 milliamp scale, a shunt must be used that will carry 49/50 of the current or 49 milliamp. The computation is the same as in step 2. The shunt resistor equals voltage divided current, which is the same voltage, 0.1 volt, divided the current, which is 0.049 amp, and this equals to 0.04 ohms. Convert the meter for the 0 to 100 milliamp scale. A shunt must be used that will carry 99/100 of the current, or 99 milliamps. Shunt resistance equals to voltage divided current, 0.1 volts divided 0.099 amps equals to 1.01 ohms. A shunt with an ohmic value of 1.01 is required for the meter to safely use a 0 to 100 milliamp range. Looking at figure 2-6, notice the switching device used to change the ranges of the meter at the bottom of the figure. The correct scale on the range dial must be used to correspond to the selected range. Caution: there are two important things to remember for the safety of your ammeter. First, an ammeter must always be connected in series with a circuit device or the power supply. Never connect an ammeter in parallel with the power supply or circuit devices. Figure 2-8, as you can see through the meter shunt calculation, the applied voltage to the meter movement coil only required 0.1 volts for full-scale deflection. If a voltage greater than 0.1 is used, it will cause excessive current to flow through the coil. This will result in damage to the coil. To make series connection usually requires breaking the circuits open or disconnecting the device in order to insert the meter. This allows the current to flow through the meter. The second thing to remember is when the current value you are testing is unknown, start at the highest meter range. This way you will not exceed the highest value of the meter scale during the reading of a circuit. As you can see in figure 2-8, the wrong way to connect a ammeter is shown first. The right way in series is shown second. Some review questions. An ammeter is used to measure current. In order to measure larger current, a shunt or alternate path is provided for the current. An ammeter should always be connected in series with the load. 2.3 voltmeter. The same basic meter movement that is used in an ammeter is also used to measure voltage. This is providing that the impressed voltage across the coil never exceeds 0.1 volts, the same as computed for full-scale deflection. This is important, always as computed for full-scale deflection. To arrange the meter to measure higher voltages, multiplier resistors are placed in series with the ammeter movement coil using a switch. A meter similar to the meter that measured current is used. Refer to figure 2-9. Voltmeters are always connected in parallel with the device being measured. Example: follow the steps as the multipliers are computed so that the meter can measure voltages from 0 to 1 volt, 0 to 10 volts, 0 to 100 volts, and 0 to 500 volts. Remember that no more than 0.1 volt is allowed across the meter coil at any time. Therefore, a resistor that will cause a voltage drop of 0.9 volts must be placed in series with the meter if the meter is used to measure 1 volt. Also, the meter will only allow 0.001 amp for full-scale deflection. This is the highest current allowed in the coil circuit. The multiplier resistor must produce a 0.9 volt drop in this case when a 0.001 amp flows through it. So the multiplier resistor calculation is multiplier resistor equals voltage divided current. Again, Ohm's law. So in this case, the multiplier resistor equals 0.9 volts divided 0.001 amp. And the multiplier resistor equals to 900 ohms. Again, this is for a reading of 0 to 1 volt scale. Step 2. To convert 0 to 10 volts range, a resistor must be selected to produce a 9.9 volts drop. So the resistor multiplier using Ohm's law equals to 9.9 volts divided 0.001 amp, which is equal to 9,900 ohms. Step 3. To convert 0 to 100 volt range, a resistor must be selected to produce a 99.9 volt drop. 99.9 volts comes from 9/10 or 99/100 of 100 volts, which is the maximum range, and 99/100 of 100 is 99.9. which is the voltage drop required from the resistor multiplier. So using Ohm's law again, the resistor multiplier equals to 99.9 volts divided 0.001 amp or 99,000 ohms. Step 4, 0 to 500 volt range, calculate, and the resistor multiplier must cause a 499.9 volt drop. Again, coming from the 500 because we only can allow 0.01 volts through the meter coil. So we have to drop 499.9 volts. And again, using Ohm's law, the resistor multiplier equals to 499.9 volts divided 0.001 amp, which is equal to 499,900 ohms. Again, a switching device is used to select the correct multiple resistor for the range in use. Read the scale on the dial that corresponds to the range selected. The dial on a meter is generally referred to as the range selector switch. Figure 2-9, step 1, the multiplier causes an IR drop or current and resistance drop of 0.9 volts. Step 2, the multiplier causes an IR drop of 9.9 volts. Step 3, the multiplier causes an IR drop of 99.9 volts. In step 4, the multiplier causes an IR drop of 499.9 volts. Bottom, the basic setup of a voltmeter. A switch is added to select the range. Caution. A voltmeter is always connected in parallel or across the circuit. To measure a voltage, the circuit does not have to be broken. See figure 2-10. As with the ammeter, when measuring an unknown voltage, always starts measuring with the meter set on its highest range. Adjust downward to the proper range to avoid damaging the meter. In addition, be sure that the leads are connected with the correct polarity. The black lead is negative and the red lead is positive. Figure 2-10, a voltmeter is connected in parallel with the device when taking voltage reading. Voltmeter sensitivity. The sensitivity of a voltmeter is a sign of quality. Ohms per volt is the unit of measuring sensitivity. In step 4 of the previous example, the total resistance of the meter and its multiplier resistance is 499,900 ohms for the multiplier resistor, plus 100 ohms, which is the meter resistance, so the total resistance is 500,000 ohms. The total amount of resistance in the 500 volt range is equivalent to the following. Again, using Ohm's law, 500,000 ohms divided 500 volts equals 100 ohms per volt. That's just a simple division to know how many ohms per volt. Divide ohms by the volts. It gives you 100 ohms per volt. Using Ohm's law, I equals E divided R, or current equals voltage divided resistance. The reciprocal of I equals resistance divided voltage. So this is the same as the meter sensitivity. Therefore, the sensitivity is equal to the reciprocal of the current required for full-scale deflection. Again, sensitivity of a meter is equal to the reciprocal of the current required for full-scale deflection. For the meter used in the above example, sensitivity equals 1 volt equals 0.001 ohm, which is the coil resistance, or equals to 1000 ohms per volt. The sensitivity of a meter can be used to gauge the meter quality. A quality meter has sensitivity of at least 20,000 ohms per volt. Precision laboratory meters measure as high as 200,000 ohms per volt. Accuracy of the meter is commonly expressed as a percentage, such as 1%. That means that the true value will be within 1% of the scale reading. Another system of rating meters is the accuracy expressed as a percentage of full-scale reading. A meter may have a rating of more or less 0.05% or less. In general, the smaller the percentage, the higher the quality of the meter. Loading a circuit. When a voltmeter is connected across a circuit to measure a potential difference, it is in parallel with the load in the circuit. Again, when a voltmeter is connected across a circuit to measure the potential difference, it is in parallel with the load in the circuit. This situation can introduce errors in voltage measurement. In meters with low sensitivity, this is very common. It is very important to keep this in mind. In figure 2-11, two 10,000 ohm resistors form a voltage divider circuit across the 10 volt source. The voltage drops across R1 and R2 are 5 volt each. If a meter with a sensitivity of 1000 ohms per volt on the 10 volt range is used to measure the voltage across R1, the meter resistance will be in parallel with R1. Solving parallel circuits is explained in depth in Chapter 7. For now, it is enough to know that the addition of this meter cuts the effective resistance of R1 in half. The combined resistance of the meter and R1 is equal to R1 plus Rm, or R multiplier. Again, R1 plus R multiplier divided by 2 equals the effective resistance, or R effective. Or 10,000 ohms divided 2 equals 5,000 ohms. With the meter connected, the total circuit resistance becomes the R effective plus R2 equals the R total, or 5,000 ohms plus 10,000 ohms equals 15,000 ohms. Using Ohm's law, the current can be calculated at approximately 0.0067 amps. Using Ohm's law again, ER1 equals 3.35 volts and ER2 equals 6.7 volts. The meter has caused an error of more than 1 volt due to its shunting effect. To avoid an excess of errors resulting from this effect, a more sensitive meter should be used. In figure 2-12, a 5,000 ohms per volt meter is used. In this case, the combined resistance of the meter and R1 equals 8,333 ohms. The total circuit resistance is 18,300 ohms. Using Ohm's law, the current, or I, is equal to 0.00055 amps, and E, or voltage, R1, equals to 4.6, and ER2, or voltage R2, equals to 5.5 volts. An error of 0.4 volts still exists, but the increased sensitivity of the meter has reduced the error.
Even more costly meters, with a sensitivity of 20,000 ohms per volt, can reduce the error to an amount that would be barely noticed. Figure 2-12, a sensitive meter gives more accurate readings. Review questions for section 2.3. A voltmeter is used to measure voltage. To measure higher voltages, multimeter resistors are placed in series with the meter movement coil. A voltmeter is connected in parallel with a device. A black lead of a meter is connected to the negative polarity of the device being red, and the red lead is attached to the positive polarity. A quality meter has a sensitivity of at least 20,000 ohms per volt. Explain what is meant by loading a circuit as it relates to an electrical meter. The load remains in the circuit and the meter is placed across the load, watching for polarity. 2.4. Ohm meters. A meter used to measure the value of an unknown resistance is called an ohm meter. The same meter movement that was used in the volt and amp meter can be used for the ohm meter. The voltage source and a variable resistor are added to the ohm meter's circuit. A series type ohm meter is shown. Figure 2-13 schematic diagram of a series ohm meter. A 3-volt battery is used as the source for the ohm meter. The battery is built into the meter case. The meter movement permits only 0.1 volt for a current of 0.001 amps for full-scale deflection. Therefore, a multiplier resistor is placed in series with the meter coil to reduce the voltage applied to the meter coil. So, resistance M or Rm equals to voltage divided current. So Rm or resistor movement equals to, in this case, 2.9 volts divided 0.001 amps. And the Rm is equal to 2900 ohms. The 2900 ohm multiplier resistor plus the meter coil resistance is equal to 3000 ohms. Part of this resistance is made up of a variable resistor to allow the total resistance to vary. Because temperature changes or weak batteries can affect the total resistance of the circuit, the ohm meter must be calibrated. Adjust for zero resistance in order to ensure the most accurate reading possible. The knob used adjusting the pointing needle position to zero is usually marked zero adjust, or with an omega symbol near it. To use the ohm meter, first short the test leads together. This applies a 0 ohms across the meter. Adjust the ohms adjustment knob until the needle points at 0. The needle should deflect from its position at rest on the left to the zero resistance indication on the right side of the scale. If the needle does not deflect, it is possible that the battery is dead or extremely weak. After the ohm meter has been calibrated to read 0 ohms when the leads are shorted, you can make a reading of an unknown resistance by placing the unknown resistance between the test leads. Caution. Before connecting an ohm meter to an electrical circuit to read an unknown value, be sure that the circuit is not energized. An energized circuit will damage the meter and can be harmful to you. Electrical energy in a circuit is not needed to operate the meter movement coil, as it is when using the voltmeter or amp meter. The batteries inside the case provide the source of power for the ohm meter. Connecting the ohm meter to an energized circuit will apply the circuit's voltage directly to the coil and battery, which can result in damage to the meter and possible harm to you. A shunt ohm meter is connected as shown in figure 2-14. In this circuit, the unknown resistance, or Rx, is shunted, or connected in parallel, across the meter. Low values of Rx cause lower currents through the meter. High values of Rx cause high meter currents. When the ohm meter is connected in the shunt position, the indicating needle deflects from left to right in the manner of the amp meter and voltmeter. Zero resistance is on the left. The scale increases from left to right. Figure 2-14, schematic diagram of a shunt ohm meter. Note that the meter reads in the opposite direction of other ohm meters. Ohm meter scales. The resistance value is indicated on the ohm scale, which is a nonlinear scale. A nonlinear scale has markings that are not evenly spaced. The nonlinear scale factor increases as the needle travels from zero resistance to infinite resistance. In figure 2-15, a typical ohm meter scale is represented. The right side of the scale is 0. On the left side is infinity. An infinity reading means that the resistance value is so high that it exceeds the capabilities of the ohm meter to read it. Notice how the scale factor changes along the ohm meter scale. On the right side, the small marks between the numbers 0 and 2 represent 0.2 ohms each. On the left side, between the 50 and 70 ohms mark, the small marks represent 5 ohms each. To take accurate readings of unknown resistance values, it is recommended that the range selector switch be changed until the reading falls on the mid-third of the scale. An ohm meter comes with a selection of ranges that can be changed by rotating the selector switch. Typical range values are R times 10, R times 100, R times 1K, R times 10K. These markings mean that the reading indicator on the ohms should be multiplied by 10, 100, 1000, or 10,000 respectively. Review questions for section 2.4. An ohm meter is used to measure
resistance.
An ohm meter uses a non-linear scale while a voltmeter uses a linear scale. You must calibrate an ohm meter before use. Yes. Why must you calibrate it? For accuracy. Find the value of the multiplier resistor Rx in the following circuit. It should read 50 volts across A to B. Using Ohm's law, R equals voltage divided current, or Rm equals voltage divided current. If Rm equals 49 kilo ohms, if Rm equals 49.9 volts divided, we know the voltage, which is 49.9 volts, and we know the current for full deflection. If we know it should read 50 volts from point A to point B, which is the two ends of the circuit, we know for full deflection it only takes 0.1 volt to cause full deflection. So Rx should be 49.9 volts, or 50 volts minus 0.1, which is 49.9 volts. So we know the voltage, which is 49.9 volts. And the voltage must be divided by current. The current is known to be 0.001 amp. So divide 49.9 volts by 0.001 amp. We get 49,900 ohms. The volt-ohm-meter, millimeter, or VOM. A common and simple multimeter used in electronic circuits is the volt-ohm-meter, or VOM. A VOM is a voltmeter, ammeter, and the ohm meter all in one. The VOM has the advantages of being inexpensive and portable. It does, however, usually have a low input resistance in ohms per volt on the lowest voltage range. This factor can cause accuracy problems. When an electronic device called a field effect transistor was developed, a VOM was designed to overcome the low input impedance problem. The field effect transistor VOM, or FETVOMS, measures AC and DC voltages, the AC and DC current, resistance, and decibel ratings. Some multimeters are also equipped with accessories such as temperature probes. The leads of the temperature probe are inserted into the meter, while the probe itself can be placed in front of an air conditioning duct near a furnace heater or submerged in hot liquid. The scale of the meter reflects the temperature in Celsius and/or Fahrenheit. The optional accessories for VOMS include adapters for reading higher than normal voltages and larger than normal meter current values. Digital multimeters. Digital multimeters, or DMMs, are the most commonly used meters in the electronic fields today. They are rapidly replacing the analog meter, which operates on the principle of magnetism and rotating coil discussed in the previous examples. The DMM uses the modern electronic circuitry to take electrical measurements and display values, usually in a liquid crystal display screen. This circuitry is beyond the scope of this chapter. See Figure 2-16. Digital meters are more rugged and smaller in size than analog meters. They also are very accurate and very portable. However, some technicians still prefer the analog meters for taking certain types of readings involving solid-state circuits. This will be explained in more depth when solid-state electronic devices are explored. The liquid crystal display shows the meter reading in digits rather than on a scale. Some DMMs simultaneously display digits as well as a bar graph that simulates a linear scale reading. Figure 2-17. Digital meters not only measure volts, ohms, and current, but also can test electronic components such as transistors and diodes. Figure 2-18. The digital multimeter can come with a rotary dial, like the analog meter, to select functions, or a keypad that is pressed with the fingertips. Most digital meters use an international standard of labels to indicate various meter functions, such as AC and DC. Combination of symbols. Figure 2-19. The graphic symbols for AC and DC are often combined with metric prefixes to identify the function or range of the meter setting. Figure 2-17. This DMM display values in a numerical form or in a graphical form. Many digital multimeters are equipped with protective circuitry to prevent accidental damage when the wrong function is used to take the reading. Not all digital meters have this capability, but it is available. Polarity is usually not an issue when using a digital meter. The meter will be automatically adjusted for an incorrect polarity. It will flash a message or symbol on the liquid crystal display warning the user of the wrong polarity. Some digital meters have an auto range feature. This means that it is not necessary to determine the range to select when using the meter. On these meters, this function is done automatically through the internal electronic circuitry. Figure 2-20. Resistance reading used in a DMM still requires you to disconnect the circuit from the power source to prevent damaging the meter. Figure 2-18, at the lower right of the selector switch of this DMM is a setting to test diodes and capacitors. Figure 2-19, the international graphic symbols for AC and DC combined with other electrical prefix symbols to indicate a meter setting. Computer display meters. Some manufacturers offer interface cards that can be installed on a personal computer and have test leads similar to meter leads. After the interface board is installed in an expansion slot in the computer, software is loaded. Now the computer will display a simulated meter on the monitor. The computer can then be used to take voltage, current, and resistance readings. Using the computer is very similar to using a digital meter, but with the computer you can use the memory and hard drive system to store measurements and retrieve them later. This type of metering equipment is commonly installed in new industry applications to monitor high-speed assembly equipment or to test electrical parts. AC meter readings. When AC is applied to the meter movement, the needle does not deflect. Remember that AC rapidly changes direction. The meter coil current changes direction and pace with the applied AC voltage. The result is that the magnetic field rises and collapses, and then reverses so rapidly that the coil cannot deflect the needle. The coil simply vibrates under the influence of applied AC voltage. To remedy this, a meter changes the AC voltage into DC by means of a rectifier. The rectifier is covered in detail in Chapter 17. For now, it is sufficient to say that a rectifier converts the applied AC current to a DC current of equal value. When the applied AC current is rectified to an equal DC value, the value is referred to as the RMS value. The abbreviation RMS stands for root mean square. This is a formula used to equate AC voltage to DC voltage. The RMS value is the equivalent DC value of an AC waveform. Many meter scales and some DMMs use this abbreviation. Some meters have a special location to plug in the meter lead when reading AC voltage or current. Many meters have a scale marking printed as RMS. This simply means that the readings taken on that scale are equal for DC or AC voltages. Resolution. Resolution is a term that describes the degree of change that must take place before the meter will display the value. For example, if a meter has a resolution of 1 to 1000, it can measure voltage down to 1 millivolt. In general, the better the resolution, the more expensive the meter. In digital meters, the resolution is also determined by how many digits the meter can display. A digital meter with a 5-digit readout has a better resolution than a digital meter with a 4-digit readout. Important meter information. Multimeters are very useful tools. There are a number of important details to remember when using these meters. A meter is a delicate instrument. Handle it with care and respect. Jarring, dropping, and other rough treatment can damage a meter, especially coil meter movements. When measuring voltage, the meter must be connected in parallel to the device being read. Start on the highest range when measuring an unknown voltage and move slowly to a lower range for increased accuracy as needed. Remember to observe correct polarity. The red or positive lead goes to the positive side of the circuit. The black or negative lead goes to the negative side of the circuit. When measuring current, an ammeter must be connected in series with the circuit. A wire must be disconnected to insert the meter. It is wise to make a rough current calculation using Ohm's law to determine the proper current range on the meter. When troubleshooting a circuit, it is best to start on the highest possible setting. A faulty component can cause higher currents that would not be normally expected. Again, observe correct polarity, red to the positive side of the circuit and black to the negative side of the circuit. When measuring resistance, be certain that no power is applied to the circuit. It is best to disconnect the voltage source before taking any resistance measurements. In general, it is not necessary to observe polarity when taking resistance measurements. However, as you advance through your studies, polarity must be observed when checking certain solid-state devices. Always adjust and zero the meter on proper range before measurements are made. The ohm meter should be readjusted after changing ranges or after prolonged use. An open circuit will have an infinite reading. On all meter measurements, make a flash check before permanently connecting the meter to the circuit. What does a flash check mean? First, decision should be made on how to connect the meter to the circuit. Then only the negative lead should be connected with the positive meter lead left disconnected while observing the meter. Quickly touch and remove the positive lead to the circuit. Did the needle move in the wrong direction? If so, polarity must be changed. Did the needle move too violently? If so, the meter range selector should be changed to a higher range. Remember, you should start on the highest range when you're not positive on the voltage or current values. The flash check will save you many dollars in meter replacement and repairs as well as wasted time. Meter has its greatest accuracy at 2/3 deflection of the meter scale. Use the range that reads as close to this deflection as possible. Often, electronic circuits are quite compact. Be sure that the test leads do not cross over 2 or more connection points, as this could result in a short circuit. Be sure that the test leads are in good working condition. There should be no frayed or bare wiring. Make it a habit to keep your fingers from touching any exposed metal part of the test lead tips and or the circuits being tested. Most of the time you'll be working with voltages that are harmless, but sooner or later you'll be working with circuits that can produce severe or fatal shocks. The habits you develop while testing low voltage circuits will be carried with you when you're working with higher voltages. Make a habit of testing circuits safely when danger voltages are present. Do not make the common mistake of connecting the meter to a voltage source without first changing the selector mode switch after checking resistance or amperage. In addition, some meters have a separate input for the test leads when in the current mode, especially when high currents are to be measured. You may have selected the correct mode of operation using the selector switch, but left the test lead plugged into the wrong meter jack. It is very important not to attempt reading from the back of a television picture tube or a computer monitor. There are extremely high voltages present in these locations, and the meter usually requires special high voltage test leads specifically designed for this purpose. Caution. When using a multimeter or DMM, it is easy to connect the meter to a voltage source immediately after taking resistance or current readings. This is the most common mistake when using a multimeter or DMM. This action will result in damage to the meter or personal injury. Electric shock. Almost all electrical systems contain a ground. A ground provides a safe path for an electrical fault and has a 0-volt potential. A ground provides a safe path for an electrical fault and has a 0-volt potential. It is typically constructed by connecting a conductor between one of the electrical system conductors and the earth. On AC systems, the neutral conductor is grounded. On DC systems, the negative conductor is grounded. Some electrical systems do not connect directly to the earth. Instead, the metal enclosures or metal conduits serve as a ground or as a return path for current. If a person touches an energized conductor, that person can easily serve as the path to ground. As shown in Figure 2-21, an experienced electric shock. Also, if a system experiences an electrical fault, the metal enclosure or conduit may have a higher voltage potential than the earth ground. Thus, a person touching the enclosure or conductor can experience electric shock. Some devices are double insulated, which means the outside enclosure is not grounded. A person using the device will not be in contact with the ground circuit by using the device, and thus will most likely not experience electric shock should a ground fault occur. Figure 2-21, when a person touches an energized conductor, his or her body completes a circuit to ground. Electric shock levels. A person can experience different levels of electric shock. These are rated by value of current flow and the effect each current value has on the human body. The values of current flow and their effects are listed in the following table. Current, 1 milliamp, is barely noticeable. That's the effect. The current of 5 milliamps is the highest harmless value, but can be painful. From 10 to 20 milliamps, there can be sustained muscle contraction. The victim cannot let go. And from 100 to 300 milliamps, paralysis of respiratory muscles can be fatal, severe internal and external burns, and can result in organ damage. 2 amps can cause cardiac arrest and is most times fatal. Lesson in safety. One of the best ways to avoid fatal electric shock is to keep one hand in your pocket while working with high voltages. This way, any current flowing through your body does not flow through one hand and out the other. The amount of resistance through a person's body depends on many different things. For example, a resistance path from hand to foot will be higher than from hand to hand, especially if the person is wearing dry shoes in good condition. Another factor is the amount of skin surface area connected to the potential. A person's skin condition is the most influential resistance factor. A person with dry skin has a high resistance of about 100,000 ohms. When the surface of the skin is covered with sweat, the resistance can be 10,000 ohms or less. Using Ohm's law and the table above, you can easily see how a person working with a 120 volt system in a hot enclosed area is susceptible to sustained muscle contraction should electric shock occur. To prove this, using Ohm's law, 120 volts divided 10,000 ohms equals 12 milliamps. The National Electric Code, or NEC, requires all electrical systems of 50 volts or higher to be grounded. This rule is to protect people from electrocution when they come into contact with components in an electrical system. A properly grounded electrical device will produce a low resistance path for current. When the properly grounded device comes into contact with an energized conductor, the fuse or breaker will automatically trip or open the circuit. Ground fault interrupter. A ground fault interrupter, or GFI, provides protection from excessive fault currents through the human body. The NEC requires ground fault protection for specific locations where there is a high probability of electric shock, such as damp, wet locations. A ground fault interrupter provides protection by monitoring and comparing the current through the hot and neutral conductors. A complete circuit has the same current in the hot and neutral conductors. If a ground fault occurs, part of the current will flow to ground. When part of the current flows to ground, the comparator circuit detects an unbalanced condition between the hot and the neutral currents. If the difference between the hot and the neutral conductor exceeds 5 milliamps, the comparator circuit will energize the trip coil and cause a contact to open in the hot conductor circuit. This stops the flow of current through both the outlet and the person holding a device that is plugged into the outlet. The electric shock is stopped almost instantaneously. After the GFI is stripped, the red reset button needs to be pressed to reset the GFI trip mechanism once more. See Figure 2-22. Be aware of a condition known as the nuisance trip, which occurs when there is excessive moisture in the device area. Ground fault protection devices are not limited to power outlet designs. They are commonly incorporated in GFI-style circuit breakers. Non-GFI power outlets can be used with single GFI type breakers. The non-GFI power outlet will then provide the same protection as a GFI outlet. This is a very cost-effective solution when several outlets are required to be GFI. Cardiopulmonary resuscitation, CPR. When working with electrical systems, there is always a real danger of electrocution. The heart may stop beating because of the electric shock. Cardiopulmonary resuscitation, or CPR, is an emergency technique consisting of mouth-to-mouth resuscitation and a series of chest compressions. The basics of CPR will be covered in this section, but you should take a CPR course from a certified instructor to be competent to administer CPR. In case of an accident, call for help. Check to see if live wires are still in contact with the victim and move any away with a non-conductive item. Check to see if the victim is responsive. If the victim is responsive, he or she most likely doesn't need CPR. However, if the victim is not responsive and not breathing, you will need to administer CPR until help arrives. To administer CPR, you will need to ensure the airway is clear. With the victim lying on his or her back, tilt the head back and lift the chin. Place your mouth over the victim's mouth and give 2 short breaths. Position your hands in the center of the victim's chest and firmly press down rapidly 30 times. Continue with 2 breaths followed by 30 pumps until help arrives. Review questions for section 2.5. What does the abbreviation COM stand for on a meter, and what is its polarity? It stands for common and the polarity is negative. What does DIM stand for, or DMM, digital multimeter? What does resolution mean when referring to a DMM? The accuracy of the measurement as displayed in the LCD. How do you connect an ammeter to a circuit? In series, by first opening the circuit. How do you connect a voltmeter to a circuit? In parallel with the load. Which of the 3 meters should not be used while the circuit is energized? The ohm meter. 2.6. Electrical diagrams. Electrical diagrams convey specific information to the technician. They illustrate such items as the size, type, component, part number, and component location in relationship to the other circuit components. Diagrams can be used for installation, fabrication, troubleshooting, or to explain the circuit's operation or purpose. Symbols are used to represent circuit components. Wires or conductors are usually shown as lines. Their connections can be shown a number of ways. See Figure 2-23. One primary type of electrical drawing you will encounter is the schematic diagram. See Figure 2-24. This is a typical schematic diagram. It shows what parts are needed and how they connect to one another. The distance between the components do not represent the actual distances. The main purpose of the schematic is to show how the components relate to each other. The diagram shows which components are in series or parallel with each other. Schematics are extremely valuable troubleshooting tools. Figure 2-23. Schematics of wires. Two wires can cross on a schematic and not be electrically connected. The dot must be shown at the intersection for a connection to be made. Figure 2-24. A typical schematic illustrates the location of the components and how they relate to one another. The combination of meters, wiring diagrams, schematics, and electronic theory allow a technician to find circuit problems. Many circuits are impossible to troubleshoot without the aid of schematics and the application of electronic theory. In Figure 2-25 is a comparison of an elementary line diagram and a wiring diagram. This illustration shows the operation of a typical stop-start motor control system. The elementary line diagram on the left is similar to a schematic. It is used primarily in industrial processes to illustrate how a system's electrical controls relate to each other. On the right is the actual wiring diagram. This would be used to connect the control system. The elementary diagram clearly illustrates how the circuit operates, while the wiring diagram illustrates the relative positions of the connection points and the components as they would actually be found in the equipment. Each diagram has its own purpose. Sometimes a block diagram is used to show how an overall system works. Look at Figure 2-26 to see a block diagram of a typical AM radio. The components, such as the amplifier, are grouped together in stages. Figure 2-27 is a typical plan of the electrical circuits to be installed in one room of a residence. Figure 2-25, both the elementary line diagram and the wiring diagram shown here are of the same electrical system, but they are presented in two different ways. The elementary line diagram is used to clearly express how the circuit works. The wiring diagram is used to install the system. In Figure 2-26, a block diagram is used to illustrate how major electrical systems relate to each other. Figure 2-27, typical layout of a residential room to be wired by an electrician. All information necessary to correctly wire the room is indicated on the plan or print. The drawing indicates the general location of switches, outlets, and lighting. Descriptions of wire sizes, switch amperages, and breaker sizes are not shown on this type of plan because the electrician is trained to be familiar with the electrical codes dealing with these factors. As you progress through the text, you will gain a large symbol vocabulary. This will help you interpret many different types of electrical drawings. This vocabulary, combined with a complete understanding of schematics and meters, will help you troubleshoot, repair, and construct any electrical systems rapidly. When constructing an electrical system, you may find using a circuit design software program beneficial. Circuit designers rely heavily on computers and software for modern electronic circuit design. See Figure 2-28. In these software programs, components can be selected from menus and placed on the drawing area. Electronic characteristics for each component, such as resistance, values, current ratings, and voltage limits, can also be added. Software systems not only can be used to draw out electronic circuitry, they can actually be used to simulate the circuit as though it was constructed with electronic components. Virtual meters can be connected to the points in the circuit experimentation and testing. A complete list of materials can be generated from the circuit design. The pattern required for a printed circuit board can be printed. This makes the design and testing process quicker and easier than if the circuit was built using actual components. Once the circuit design is tested to satisfaction, the circuit can be built using the actual components. Review questions for section 2.6. What is a schematic? It is a drawing that can show an electrical circuit for building, operation, or troubleshooting. What are the symbols used for?
To represent electrical or electronic components on a diagram or a print.
Name 3 typical electrical drawings and the use of each. A block diagram shows flow, how the system operates overall. The elementary wiring drawing clearly expresses how the system works. And the wiring diagram is an aid to install or troubleshoot the system. Summary. Analog meters use a scale with continuous variable values. Digital meters give values in discrete amounts in units 0 through 9. The basic meter movement used for many analog instruments is the moving coil galvanometer or the D'Arsonval movement. 3. It is vital to observe correct polarity in the use of analog meters. 4. Linear meter scales have evenly spaced marks. Ammeters and voltmeters use linear scales. Non-linear scales do not have evenly spaced marks. Ohm meters use non-linear scales. Ammeters measure current and are connected in series in a circuit. Shunts are resistors connected in parallel with ammeters to increase the range of the meter. Voltmeters measure voltage and are connected in parallel with the component to be read. The multiply resistor is connected in series with voltmeters to increase the range of the meter. The sensitivity of a meter is an indication of its quality. Sensitivity is measured in ohms per volt ratings. Another system of rating accuracy is based on percentage of full-scale reading. When a voltmeter is connected across a circuit to measure potential difference, it is in parallel with the load in the circuit. This situation can introduce errors in voltage measurement. A meter used to measure the value of an unknown resistance is called an ohm meter. Ohm meters are connected across the resistance being measured. A multimeter is one instrument that will measure a number of different types of values, such as current, voltage, and resistance. Digital meters are rugged, small in size, accurate, and portable. There are a number of different types of electrical diagrams. They include schematics, wiring diagrams, line diagrams, and block diagrams.